Hello, everyone. Thanks for joining this talk. So we are going to explore going beyond basic RAG with agentic behavior today. How many of you have used RAG before or heard about it? How many of you have worked with agents? I mean, they don't need to be in production, but like at least you worked, you tried, you know kind of about them. Okay, like almost the half of this audience. So I think we will all learn lots of things in this presentation. I mean, I hope so. I wanted to like put lots of information in that. So let's start. First, a little bit about me. My name is Bilge. I work as a developer relations engineer at DeepSet for almost 3 years now. I started my career as I studied computer science, then I started my career as a front-end engineer. So I was using React and TypeScript. Then I did my master's in artificial intelligence, and that's how I got into the space. But like I was already in the space before ChatGPT, so it was nice to see how ChatGPT changed the whole field. So very interesting times. I am currently based in Berlin, Germany. I just moved here, so it has been only 2 weeks. I was also here at this conference last year. I also had a talk. It was about RAG back in the days. And I'm happy to be at this conference again this year and hope to be here again next year and the year after and the year after that. Hopefully, the organizers will agree with me. All right, so here's today's agenda. First, a little bit of refresher around retrieval-augmented generation. Then we'll talk about agentic behavior. Then we'll go a bit technical, hands-on, and discuss how we can implement agentic RAG. And I will show you a demo in the end if we still have time. All right, retrieval-augmented generation. So if you ask me, retrieval-augmented generation is just a very sophisticated way of prompting. This is how I would describe it. Basically, instead of just passing the query to the large language model, so the middle, the brain in the middle, you just provide it with some instructions and some relevant context, and then you pass the prompt to the LLM, and you get a response. This makes sense because in this approach, you use LLM's generative capabilities, so not their knowledge. And you augment the LLM with the retrieval step. So the name Retrieval-Augmented Generation, it actually comes from this idea. And you grant the generative model's output in real-world data, so the answers stay factual and relevant. And some use cases for RAG are customer support frequently asked questions, enterprise knowledge bases, search engines, and question answering. So basically, anything around like question answering, RAG is a great approach, great architecture if you want to put it in your product. And funnily enough, it's still one of the most production-used architectures. So in our customers, they are still using this architecture a lot, and they are taking this applications a lot to production. And here are some benefits of RAG. First of all, I get to use my private knowledge. So if I have a data, if I have a document, if they are not publicly available, I can use this architecture and do some generative tasks on my own knowledge. And since I do retrieval in runtime, I always get up-to-date information because I can always put most up-to-date information to my database and retrieve it. And this also helps with the hallucination because since I will always have the updated data, my LLM will always have the most up-to-date information. So if I ask like the latest news about like Germany, I will always get most up-to-date information. And since I don't need to train my LLM, my language model, let's say, with my data for this approach, it's very cost-effective. So you don't need to think about like retraining the model, how to like do this training, etc. You just put your data into your database, and it's also transparent. So you know, large language models are quite like a black box, so you don't always know why they generated that answer. But with this approach, I always know the context, so I know why the LLM generated that answer. But RAG is not a solution for every problem that we have. For example, complex user queries often need multiple retrievals or deeper reasoning, such as like if you think your application, your RAG application, is a suitable architecture for this question, compare product A and product B using customer feedback, maybe your approach is not enough, because with like those type of queries, it makes sense to make some like query decomposition, retrieve information relevant to product A and product B separately, and then merge them and create like a comparison in the generation step. And sometimes initial retrieval doesn't provide enough context. I might need to go alternative sources, maybe to, like, if I'm doing some retrieval over my database, maybe it makes sense for me to go to my Slack to retrieve more relevant information around that. And since I also don't have the self-reflection in this RAG, I don't know if I retrieved enough context or not. And sometimes I need dynamic and iterative search strategies to enhance accuracy, such as like query writing or other retrieval strategies, such as like hybrid, hide. And of course, like if you have worked with RAG before, probably you can add some items to that list. And this is when agentic behavior comes handy, actually. But before understanding the agentic behavior, I think we first need to understand what an AI agent is. So there are different definitions around that. I think like nobody has a consensus on like exactly what an AI agent is, and there are definitely very complex definitions. But for me, this makes the most sense. An AI agent is a system that autonomously pursues a goal by interacting with its environment and using tools. So I want to emphasize on the system, interaction, and tool usage. So basically what an agent does is when there's a human input, it takes an action, it observes the environment, and it gets the feedback. And based on that feedback, it decides, oh, do I need an extra tool call, or can I, like, is it end? So did I reach my goal? So basically what this is, like in the simplest form, what an AI agent does. And here's another depiction of an AI agent. This is from Lillian Wang's blog post written almost 2 years ago, but I think it's still very relevant. So you see agent in the middle, and there are different components like planning, action, tools, memory. In the planning section, you see like reflection, self-critics, chain of thought, sub-goal decomposition, and the agent takes some actions by using those tools, but you see there's also direct arrow to action, so it doesn't always have to use the tools. Okay, so like now that we know what an AI agent is, now we can define what an agentic behavior is. So it's basically giving the model the ability to choose what to do next. So we kind of let LLM to decide. And how we reach that is to incorporate, by incorporating some agentic components to our AI workflow. And these agentic components, as we see like in a couple slides before here, a decision-making LLM, that's very important, a reasoning step, a self-reflection, tools, and memory. And not all of them are necessary to have this agentic behavior, but they usually come in a package. So if you want to have the minimum agentic behavior, you usually need most of these. And the biggest part of the agentic behavior is planning and action. And there are some prompting strategies around that, like chain of thought and React. But now it's mostly around tool calling term we will hear about. So let's go into that reasoning and the self-reflection part and like unpack these strategies. The main one, the first one, I must say, is chain of thought. So there was a paper written like 3 years ago, and here they were discussing how we can kind of teach a language model how to reason. And this is a standard way of prompting. Basically, if I have a math problem, Roger has 5 tennis balls. He buys 2 more cans of tennis balls. Each can has 3 tennis balls. How many tennis balls does he have now? So when you look at this question, it's not very complex for humans, but it might be a bit complex for language models. So we provided this example as the first shot and say like the answer is 11. Then we ask our real question. Say like the cafeteria had 23 apples. If they used 20 to make lunch and bought 6 more, how many apples do they have? And the model output is just like 27, which is a wrong answer. But we cannot blame it because in the end, it's just predicts the next token. So it doesn't really know how to do math all the time. But instead of doing the standard prompting, we can just add a little bit of touch here and kind of show you how it needs to think. So instead of just passing the answer, we just hint the LLM on how to reason. Here we say like Roger started with 5 balls, 2 cans of 3 tennis balls, each is 6 tennis balls, so 5 plus 6 is 11, so the answer is 11. And when we do it, this model output is now better because now it goes step by step. And as I said, like the easiest way of getting this reasoning with your language model is just leaving the prompt with, let's think step by step, and let it think, basically. But this chain of thought was not exactly enough. That's why there was another prompting strategy, React. It's combination of reason and act, and it came quite handy, especially in very complex tasks. So in this, there was also another paper around this. So Hotpot QA, in the first example, is like complex questions that require some sort of reasoning and observation, even for human beings. So the question was, how many rooms are in the hotel that is home to the Cirque du Soleil show, Mr. Meister? And the Hotpot QA label, so if you directly ask this question to an LLM, it like generates an answer, but it's mostly outdated. So what we do with this prompting strategy is, again, we try to teach the LLM how to reason, how to think, and how to also observe the answer. So let's go over the steps one by one. In the first one, it starts thinking, I need to search Cirque du Soleil show, Meister, and find the hotel. It makes a search in Act 1, but it cannot find the relevant information. So it thinks, okay, to find the hotel, I can search Meister, Cirque du Soleil, and it changes the query and makes another round of search. And this time, at least it gets the hotel name. And in the third round, it thinks, okay, I know the hotel. I can just try to find the number of rooms. And this time, it makes its search accordingly, and then it gets the result. So this whole idea of reasoning and acting is basically kind of like tool calling, very similar to tool calling. And back then, of course, this was the very early start of LLM, so LLM-based agents, and we were using prompts like this. So we were instructing the LLM to, there will be a human input coming, and what I need you to do is split it into smaller tasks, and here are the tools that you have access to. And we were parsing the tool names with descriptions, like I showed in the blue here, into the prompt. Then we were also telling LLM how to think. So we were giving instructions again, like I did in purple. So it was this is your thought process. This is the tool that you need to use, tool input. So we were expecting LLM to fill in the blanks, basically. And we were also expecting it to observe. Yeah, here. And we were allowing it to do it multiple times. And when it gets a final answer, we were expecting it to return the final answer to us. But As you can imagine, this was a lot of like depending on the LLM and the output of the LLM. We were like trying to retrieve, like extract the information from the LLM with regexes and stuff. So this was quite messy and not very production ready at all, because how can you trust the LLM to like exactly find the tool name and exactly find the tool output? Because if it makes a mistake in the text, then you cannot generate, like you cannot extract that information from the response anymore. So it was like very messy. That's why now we have tool calling. So tool calling refers to the ability of a language model to dynamically invoke external functions and APIs as a part of its reasoning process. It comes from the React idea, so from this idea, but it is more structured, because it's provided by large language model providers. So basically what we need to do now is to pass the prompt and functions that we have that we want to use as tools, like provide some information around them, like names, description, parameters. And every time when there's a new query to the LLM now can decide whether it needs to go and like invoke a tool or not. And if it decides that it needs to invoke a tool, it returns the function name and JSON object for its arguments. And then we can get these arguments and use them to call the function. And like these are the logos of like some model providers that are supporting this approach, but I'm sure there are more of them. So here's the detail. So imagine that we have this getWeather function that we can use to get information around weather by passing the latitude and longitude of a location. And then what we do next is we define the parameters. So we say that it's a function, and we say that it has the name of getWeather. We provide some description, so we can get current temperature for provided coordinates in Celsius, and then we pass the parameters and the types of parameters, the types of these parameters, and we pass we say if they are all required or not in this parameter schema, and then we pass this information to our LLM client. So this time I use OpenAI. As I said, you can use also like Cohere, Anthropic, open source models. They mostly work in that way. So when there's a query coming from the user with what's the weather like in Paris today, my LLM this time can say that, oh, in order to answer that question, I need to do a function call or tool call, and this is like what we get in response. So here it says like, oh, I need to do a function call, and in the function parameter it says the name of the tool that it needs to use, because imagine you have like tens of tools, it needs to pick the right one, and it also passes the arguments that I need to use to invoke that tool, and here I get them. So what I do next is just I parse this JSON and call my function here to get the relevant information. All right, so this is the whole like agentic behavior and RAG approach, and let's like combine them all. So what we are gonna do is to, by doing some agentic RAG, we will change the deterministic behavior of our RAG and make it a bit non-deterministic. Because if you remember the RAG picture that you see, it was very sequential. So it was like the steps were defined, so you were just doing like retrieval, prompt, and generation. So there was nothing left to the LLM. But this time, we will use LLM as the brain, and it will decide on the next action. So it can access the tools and can go to alternative resources such as web and other databases, or it can decide to update the retrieval part by doing query rewriting, query decomposition, or multi-step retrieval. So these are just like some examples. And for that, we will use Haystack. Haystack is the open source AI orchestration framework by DeepSet. And it's also the backbone of the AI platform, DeepSet AI platform that we have. It provides the tools that Python developers need to build real-world agentic AI systems. And in Haystack, there are two main building blocks, components and pipelines. And components are a smaller unit. They only have one responsibility, like embedding data or generating text, retrieving information. Maybe if you're using Haystack for indexing part, it can do chunking, lots of different stuff. And by connecting these components, these small nodes to each other, you create pipelines. And pipelines in Haystack are directed graphs. So that comes quite handy. And a little bit about Haystack ecosystem. So it's widely used by the community. So we have a big community. It has 21K stars on GitHub. And it has more than 160 components that you can just like take off the shelf and start using. It has 70 integrations. So this means like 70 different companies or like tools that you can use with Haystack, such as like model providers, evaluation tools, monitoring tools, etc. And if you are just a beginner, if you are trying to like learn how to use stuff, how to implement stuff, there are 70-ish tutorials and recipes that you can take a look and like learn. All right, so this is a component in Haystack. So each component in Haystack is a Python class that comes with this component decorator. And in this class, the only thing that you need to have is a run method in order to use that in Haystack. And in this run method, you can do anything you want. And since pipelines are graphs, you can think about components as the nodes in that graph. And by defining this run function, what you do is you actually define the inputs of that node and the outputs of that node. So for example, here, I have one input, two inputs, and both of them are strings. And I have one output that is, again, a string. This is like a very simple way of creating a component in Haystack. And as I said, by connecting these components to each other, you form the pipeline. And pipelines are a graph, so you can have loops and branches and merge those branches. So if you have a conditional things that you want to incorporate into your pipeline, it's quite possible. And I said like there are more than 160 built-in components, but if there's a specific tool that you're using or very custom logic that you want to incorporate, you can do so by just creating your own component and put it into your pipeline, basically. And this is the pipeline that we are going to build today. So in this pipeline, what we do is so there will be a user query and our chat generator, so the component that we have to connect to the model providers, is going to take a look at the user query and decide on some actions. And this router will get that response and checks if it's a tool call, it will send it to the tool invoker, and the tool invoker will invoke the relevant tool and pass this information back to the chat generator. And if the response coming from the chat generator is an assistant message, so it's just like a text, so it's not a tool call, then the router will return it to the user as the final answer of this pipeline. But since this is a very common pattern, especially if you want to build anything agentic, we wanted to like create a super component around this, basically encapsulate this thing into something that we call agent. And this agent component is kind of looks like a black box, but in the end, it's just another Haystack pipeline. It gets the user request. It can call a tool, and it can generate an answer. Or maybe it thinks that it doesn't need a tool call to resolve that query, so it will just return its own response. And as a tool, you can use lots of different things in Haystack. So you can just define your own Python function and pass it as a tool to your agent. You can use other components in Haystack by this component tool class. Or if there is like an MCP server that you want to try, you can incorporate the tools coming from those servers with MCP tool to your agent. And if you want to do some tool management, so group those tools in some way. You can use also the tool set class that we have. And the good thing about this agent is like you have the full control. So it's LLM model provider agnostic. You can try OpenAI models and decide to switch to an open source one, or try this new shiny model from Anthropic. So you are in charge of that. And you can, again, define the system prompt. This is also comes quite handy. And in the demo, I will also show you how to do the observability in the agents. And for that, I will be using LangFuse. And we will see like the reasoning step and the tool calling step of the agent on every step. All right, now we can switch to the demo. Let me see if I can do it. So let me make that a bit larger. Yes. So I already run this demo, so I don't trust like LLMs fully, at least like for these very basic use cases, and I didn't want to take the risk to run everything here. But you will see everything and every output in this Collab notebook. So I love Collab notebooks because they are reproducible. Like if there's something is not working, it's probably like just the haystack code, so it's not about your environment, and it's nice to share the code. So first, what I do is I enable tracing because I want to do some sort of observability over my agent. And then I install relevant packages, Haystack AI, and LangFuse-Haystack package, which is the integration of LangFuse for Haystack. And then I provide the keys. I will use OpenAI, so I will give that key. I will use web search too. So for that, I will be using SerperDev. And I'm also passing my LangFuse API keys here. If you're familiar with LangFuse or like other observability tools, they usually need these API keys if you want to use their cloud version. And here is like the search component that I will be using, but just for the sake of simplicity, I wanted to just show you how it works. So if you initialize this component and say that like I want to have this top 5 relevant documents and run a query, it just goes to web and retrieves the most relevant 5 links from Google. But it doesn't get the full content of it. So it just like, imagine you're just looking at a Google search page, so you don't have the full content. But when I did that, it returned me these like 5 documents here. And each document, as you see, it has a content. It just, so when I asked like when did Berlin buzzwords start, it gave me this like 2009 answer here. And in the meta, you see the title of that page and also link of that page. So this is how you would use this component. Now what I will do is I will use that component as a tool for my agent. And for that, I will do something tricky. Not like tricky, but like more like a workaround. So I will write a function that will just like get the document context here. Like we have like document content here and here, and like parse it as a string. So this is what I do in this docstring function. And when I initialize my component tool, I pass the SerperDev web search as my component. I define a name for that. I define a description. This is like I do for this is what I do for tool calling. And the nice thing about this component tool is like I don't need to define the parameters because this class will already know it from this component. So I don't need to think about like, oh, what do I need to pass to this component? Is it like a query? What's the type of that query, etc. It's handled automatically. Then I parse every output of that component into a string by running over docstring, and I save it to the agent state as documents. Then I use that component again, but this time I limited allowed domains with Wikipedia. So I adjusted this tool basically for wiki search and said like you only need to use, you can only use this for like Wikipedia. And if you need some information from Wikipedia, use this one, or for other stuff, use this one. So this is what I will do for my agent. And I do this outputs the string again, like I did here, and outputs the state. OK, then I start initializing my agent. First, I create a connection to LangFuse with under the name of Agentic Reg Demo. This is a game. This is a name that you can give. And here is my agent component. So first, I define the model, so the LLM that I think that should act as a brain. And here I go with GPT-4o Mini. It's a cheap model, relatively cheap model, and it's good at tool calling. Then I define the system prompt and say that you're a research agent that can find information on web, or specifically on Wikipedia, and answer questions. Use Wikisearch tool if you need facts, and use web search tool for latest news on topics. Then I provide some more information and say, like, only use the retrieved context, yada, yada. Then I give the tools here, and I define my state. So I want to save all the documents retrieved from web, because I want to, in the end, see if it's grounded or not. And I also provide a streaming callback. This is important, especially if you want to log and see what's going on in your application. OK, so what I do as the last step is I run this RAG agent with this query. So can you tell me about Florence Nightingale's contributions to nursery? And in the streaming, I see that it makes a tool call. It calls this Wikisearch tool with this query. You see that it's not the same. So the agent itself kind of adjusted it to get better information. Now I got some results from web. I see their links and I see their content here. But it thought that it's not enough. So it changed the query a bit, again called the same tool. Now it got a different there are some overlaps, but different list of documents. So this time, for example, it has history of nursing in the United Kingdom. And by taking a look at both of these document lists, it generates an answer for me. And I tried another query, and I said, summarize the financial and environmental impact of coin mining. And this time, it made two tool calls at the same time. But it went to web search, and it said, first I need to do financial impact of cryptocurrency mining. Then I need to also search for environmental impact of cryptocurrency mining and combine that information to come up with the final result. And here we see the documents that we got for both of those queries and its final response. You also can get the final response by parsing the last message coming from the agent. And since we saved everything in our document state, I can also see the list of documents that I use and maybe return that as a source to my end users. And let's see how this looks on LangFuse. So it has a UI like this. Maybe let me try to make it larger. OK. So you see there's this Agentic Reg demo, two of the queries that we use. Let's take a look at this one. So here I see Agentic Reg demo. And this whole query for me, for example, it costed this much money with the model that I use. And I also get information around the latency. So I here, for example, see the same query that was used to call Wikisearch in my first query, and I can see the results here. And basically this is passed to the chat generator again, and the assistant decided that it needs to make another tool call here, and this time use this query. And here I see another tool call to the Wikisearch, and I see the final response of my model here in this span. And if we take a look at the other one, one thing you can pay attention is here it goes model tool call, model, tool call, and model again. So it's like an iterative thing. But if you take a look at the other query, you see that it goes to the model, then it decides, okay, 2 parallel tool calls. They are like not related to each other that I can do like in separately, and another model. So if you take a look at these, I see again like it's a function call to web search and financial impact of cryptocurrency mining and environmental impact of cryptocurrency mining. And the model generates the answer here in this form. And yeah, as again, here I can see the total cost of it, the latency of it. So this comes quite handy on development and in production as well. All right, back to this. That was all that I wanted to share with you. If you're interested in like getting the presentation and the material around this presentation, you can scan this QR code. And if you have any further questions, you can also like find me on LinkedIn. But I think we have some time for questions. So if you have now, I can answer them. Thank you.
Thanks a lot for your talk. And I get you the first question.
Thank you for the talk. You already said that you're not trusting any LLM. If you're just chaining like different tools, you can get like an infinite recursion. So of course it would be easy, straightforward to implement like a circuit breaker. But is there any kind of functionality that you nudge the large language model behind it to don't do now an additional research step? Maybe you answer now, and then a little bit later in the next iteration, now you should really answer. So is there like granularity to steer the behavior?
So without doing that, you can limit the number of loops that an agent can have. So you can say like, only do, I don't know, like 5 iterations. If you think that you're passing, like don't do the 6th one and just stop and like give me the response. This is like one thing that you can do, as you said, like breaking the circuit. But I think that the better way of doing that is in the prompt. But then you also, as a human, need to think like, okay, when do I want my agent to stop, this loop to stop? If you have a clear definition of that, and if you put that into your prompt, the agent will be able to, or the LLM will be able to understand that. But if it's still an ambiguity for you, then it will not be also very clear for the large language model to like, okay, what is enough context for you? If your business case is suitable for that, yeah, putting into the prompt is the best option.
All right, thank you. Do I see more questions? Maybe people need some time to think about it. Yeah. We don't have online questions.
All right.
Okay. Thanks for your talk.
There's some.
We have one. Okay. Great.
Thank you for the talk. Could you talk a little bit about latency? So, like, as any agentic system, when you're doing multiple rounds, like asking LLMs, it just spikes latency a lot. So, how do you have like any ideas how to approach this problem? Like, if you're building a chatbot, like people will not be waiting like maybe a minute for an answer. So,
yeah, great question. So, in the generation part, what we do in Haystack is to be able to do everything as async as possible. For example, for these tool calls, they can run like in separate threads, basically. And this is something that we incorporated like as something new. So like, I don't think I can, yeah. Like for this one, so this is something that that is new and that can help with the latency. But overall, yeah, I think like making the prompt as short as possible can be a trick here. But yeah, this is one of the biggest limitations at this point. But so far, like with our customers, we don't see any issues with the latency. If you can like do the retrieval good and like pass as most relevant information as possible to your model, then the latency will not be that high. Yeah.
All right. Thanks for your talk.
All right.
And maybe there's more questions over coffee for you.
Yeah. Thanks everyone for joining.